Hello, we're Group 13, and this is our presentation for our senior design project. The project that we're working on is Go Baby Go, and our team members are Brandon, Muret, Nafisa, and Samantha. First, we're gonna go over the motivation behind this project. So I'm gonna explain briefly about the Go Baby Go program. So Go Baby Go is a national community-based research, design, and outreach program that provides accessible, inexpensive, and common sense solutions for individuals with limited mobility. So one of the solutions that they came up with was to modify a ride-on car. That this will drastically impact the children's lives by providing them with the ability to move by themselves. So this modified Power Wheel cars actually lack of a lot of essential features, and that can be difficult for the parents and children to use. So this is why we're modifying the cars and working on this project. So for the sponsors and advisors for this program, first we have Dr. Jennifer Tucker. So she's the program director for Go Baby Go, and that's under the UCF Department of Physical Therapy. Our advisor for this project is Dr. Felix Soto Toro, and he's with the Mechanical Engineering Department here at UCF. Our project requirements were set by our sponsor and our advisor and consist on the following. The Go Baby Go car should have an alternative steering mechanism which will help the child manipulate the car, a remote control steering option for the parents. This feature is mostly for safety reasons in case they need to stop the car. We will also need an augmentative communication. We are required to include collision sensors. This is to prevent the car from crashing and ensuring the safety of the driver. Zero radius turn on the wheels. Record data for the program, and also make proper documentation for future cars that may be built on based on our design. Next, we're gonna talk about the goals and the objectives of this project. We're going to be working with four mechanical engineering teams to develop and modify Go Baby Go kart for four different children, and each one has a different disability. So essentially, there's two types of teams. So one is going to be the mechanical engineering teams. They are currently working on designing and developing the structure of the car. And then there's the computer engineering team, which is our team, and we're designing and developing the electrical system that's going to go on the cars. Another objective that we have is to develop an electrical system that can be attached to a Power Wheels car that allows the user to safely drive the car without any assistance. Also, this system is going to include sensors to ensure that the child is safe from obstacles and an alternative steering mechanism to accommodate for the child's specific disability. Then we're also going to develop two different web applications. So the first one is going to be a web application that the parents can use in order to remotely control the car. This is just in case of any emergencies. And the second application is going to be for the children, and they can use that application to communicate with other people. So it's a flashcard application. Next, we have the specifications for the project. So for this, we're gonna have the system has to detect the obstacles within a 200 centimeter range. The car will automatically stop when an obstacle is less than 25 centimeters away. The car will come to stop within 2 seconds if it loses the connection to the parent's application. There will be a Bluetooth module on the car that the parent's application can connect to from 100 meters. The car will be controlled by the application with less than 30 milliseconds delay. The overall system will have an installation time less than 2 hours. The car will record data of the start and the stop times, and the child application will give the user the ability to create flashcards in order to communicate with other people.
Right here, we have our overall block diagram. In the middle, we have our processor. And on the left of that, we have our distance detection sensors, which will be able to detect obstacles and will be powered through the processor. We also have a steering system block, which consists of using either a joystick or a button based on a specific family's request. And that will be able to steer the car around. Up top, we have a motors block for the different types of motors that will be used in this car in order to move the car forward, reverse, left, right. And the motors block and the steering system block will contribute to the wheels. We also have a Bluetooth connection block that allows the parent's application to communicate with the car, essentially being a remote control for the car. And as you can also see, the parent's application will be able to communicate with the child's flashcard application as well. The block's colors correspond to who is responsible for that specific part of the design. And the few blocks that are not colored, like car battery, wheels, DC power source, that's basically areas that we didn't have to design anything with. We're just using the parts and the design that comes with the specific power wheels vehicle that Go Baby Go gives us. Uh, for our distance detection sensors, we need to select sensors that are able to detect obstacles from various distances at high accuracies. We were ultimately deciding between ultrasonic and infrared sensors, and we ended up going with the ultrasonic sensors. The main reasons we are choosing this particular sensor is that it can be used in different environments, which is beneficial because some of the families either use their car uh, will either use their car specifically indoors or exclusively outdoors in a park, for example. These sensors particularly can also detect obstacles from longer ranges and can detect hard objects like walls and doors, which is very beneficial for indoor use. Also, ultrasonic sensors have a overall lower power consumption, which allows the child to use the car for longer periods of time between charges. And another small advantage is that we have more experience with using ultrasonic sensors, so we feel more comfortable implementing these in the car system. There are a few ultrasonic sensors that we were debating between, and we ended up choosing the HCSR04 sensors, which you can see here on the right. The main deciding factors for this sensor is that it has a low cost, which is advantageous because each of these cars will end up using around 6 to 10 sensors, and a higher unit cost could potentially make the system very expensive. The Go Baby Go Foundation specifically wants to reproduce this system for future cars. So it's paramount that we try to save money where we possibly can without compromising on safety features or design features. Another added bonus to this particular sensor is that our team has extensive prior experience with these sensors, and we feel very comfortable coding them. We know the ins and outs of these sensors, and there's also a lot of documentation with this particular sensor. The way we plan to implement these sensors is that they will be placed on the front, back, and sides of the car, as you can see in this diagram. Since the particular sensors that we're using has a viewing angle of 15 degrees, we plan to place multiple sensors on each side. We are estimating between 6 to 10 sensors. There are around 4 different cars that we are building our system for, and each of these cars has a different length and width. So we'll be working with the specific mechanical engineering teams and deciding the number of sensors the number of sensors that would be best for each car. We have coded up an algorithm specifically where if a sensor will detect an obstacle within 25 centimeters of the vehicle, the processor will send a signal to the braking system and will stop the car to ensure the safety of the driver. Then the driver, whether that be the child or the parent through their remote control app, will need to drive their car away from the obstacle at a distance larger than 25 centimeters. Another requirement from our sponsor was that we use alternative steering mechanisms for the car. A lot of the children's disabilities prevents them from using a traditional steering wheel independently, and a lot of the times in previous iterations, the parent would need to bend down and help the child steer their car. So specifically for one of the kids that we're designing a system for, their parent requested a push button so that the child can just push down on the wheel and move forward. And when they release, they would essentially brake. The parents decided that their child was too young and would not be able to drive the car in reverse. So we are excluding that feature from their design, but through the parents' app, they will be able to drive the car in reverse. After talking with the mechanical engineering team that's responsible for the child's family and their car, we decided to use an arcade LED button with a 100 millimeter diameter and place it in the middle of the wheel, as you see on the right here. And we specifically just used the color red because that was the child's favorite color.
Originally, the Go Baby Go cars that we saw use a single button at the center of the wheel to control the car. Pressing the button caused the car to accelerate forward, and releasing the button would cause the car to come to a stop. Some of the children were not able to turn the wheels, so they had little control over the vehicle. Normally, the parents would assist in some way turning the car. This is one of the first things the families requested be changed. They asked for a secondary controller for the movement of the car. We opted for a joystick. The idea is pretty simple. Pressing forward on the joystick would accelerate the car. Letting go would stop the car, and pulling back will increase the braking power. If the joystick's held in the back position for a long enough time, it would cause the car to reverse. Turning the joystick left or right would then also rotate the vehicle's wheels. The joysticks that we're using are 2-axis analog joysticks. They receive a 5-volt signal, and then 2 potentiometers vary the voltage based on how the joystick is moved. A lower voltage is then sent back. With the analog to digital converters that the Atmega chip offers in combination with the Arduino interface, we're able to turn these lower voltage values into integers that we then use to determine how to move the motors with pulse width modulation. Most of these joysticks are also inexpensive and offer little physical resistance, making them perfect for the kids to control. We also currently have plans to 3D print different handles to offer more leverage and control over the joystick input. Right now, the cars only support a forward motion. The user presses the button and the engines turn, accelerating the car forward. You can't reverse the cars. The motors that they are using are brushless DC motors, so applying a current through one terminal makes it turn clockwise. Applying the same current to the other terminal makes the motor move counterclockwise. We also want to be able to turn the cars left and right based on the input from the joystick, which is a similar operation. So we needed a circuit that can reverse the current based on the input from the joystick. An H-bridge is the best option for this. 4 transistors connected in a bridge pattern, where applying power to 2 of the transistors causes the current to flow in one terminal of the motor and out the other. Applying the same current to the other 2 transistors reverses this operation. We had several options for our H-bridge. In prototyping, we used pre-built ones, the IBT2 Arduino drivers, because they were rated for up to 24 volts, but we wanted to integrate these into our final circuit board. Originally, we tried to use the same open source design that the IBT2 uses, but the integrated chips that they use are not readily available. We looked at building our own out of 4 transistors, since all that is required is that the transistors be rated for 24 volts, as this is what we expect the batteries for these cars to be. But this is tedious and error-prone. Texas Instruments offers a chip, the DRV8841, that is designed for 2 motors and supports up to 48 volts input. The cost of this fits our design, so we opted for this. The families also requested some kind of range communication with the vehicle. They specifically wanted the ability to turn the cars on and off from a distance, and make minor course corrections as needed in case the kids start to turn into something they shouldn't be. We looked at 2 possible options for this, Bluetooth and Wi-Fi. We found that Wi-Fi offered more data throughput, but also consumed more power and had a limited range. Using Wi-Fi also required that we use a separate transmitter, such as a remote control, that the families could use to control the car. This increases how complicated our board would have to be, and also requires that we make a second board for the families to use. Bluetooth is a more accessible technology, as it only requires the families to have a smartphone with Bluetooth capabilities. We just have to increase our scope to also build a program that can communicate with a Bluetooth device. Bluetooth has limited data transmission, but we are only transmitting a single command at a time. Turn, stop, accelerate, or disable the vehicle. We ultimately chose Bluetooth as the more compact solution. We looked at 2 Bluetooth modules, HC05 and HM10. The HC05 is more readily available and cheaper, and uses an older version of Bluetooth, which makes it more compatible with devices, but has a higher power consumption. The HM10 uses Bluetooth 4.0 low energy, which means it uses less power while being limited in what device it can communicate with. Older phones may not be able to communicate with the newer Bluetooth standard. And the Bluetooth low energy device does not transmit a signal all the time. It only transmits data when it has to, and it only turns on when it has data to transmit. Using Bluetooth 4.0 also gives us the option to use Web Bluetooth API that Google and Mozilla have been developing for Chrome and Firefox, meaning we can build a web application to control a device and make it platform independent so it can be used on both Android and iPhone devices. Because the advantages of Bluetooth 4.0, we chose the HM10.
For the specific microcontroller for the PCB, we were debating between previous MSPs that we all had used in class and labs, but we are ultimately choosing the Atmega 328P. The main advantage to using this microcontroller is that it is the same one that's being used on an Arduino Uno, and our whole prototype has been built using that particular Arduino. So we essentially are very comfortable with programming this microcontroller, and we're very familiar with the language that has to be used. And another great benefit is that a lot of our previous code from our prototype can just be reused with this microcontroller, and that would save us a lot of time and energy. Other small advantages of this particular controller is that it has a low cost and it has a high output current per pin, which comes in handy with some of our peripherals. Our sponsor, Go Baby Go, suggested that we develop zero turn radius for the cars. And essentially, a zero turn radius is when the turning radius of the vehicle is 0 inches. The main audience for this car will be children 6 and younger, and they are still developing their spatial awareness. And Go Baby Go had noted that these children had a lot of trouble judging the amount of space needed to make a turn with a regular power wheel cars. So essentially, a zero turn radius car or Go Baby Go car would be able to turn within its own footprint. The way we are implementing this feature is we are implementing a skid turn with our car. As you see in the diagram on the right, which is what a Jeep Hurricane uses, when you steer the car in a certain direction, the wheels will turn in different directions, essentially skidding. A few of the Go Baby Go cars that the families have are four-wheel drive, so they essentially have 4 different motors. So we would be programming that whenever the joystick is pressed in, our wheels would turn in opposite directions in order to have that skid turn. We are working with the mechanical engineering teams to ensure that the traction of the wires is not affected by these skid turns, and whether there might be some other alternatives of wheels that we can use, such as caster wheels.
This was our original prototype for software development. A 24-volt DC power supply was ran through an Arduino IBD2 H-bridge to power a DC brushless motor, with inputs coming from the microcontroller on what the bridge should do. The microcontroller read inputs from a sensor, a joystick, and a Bluetooth module. The most complicated being the Bluetooth, since Bluetooth doesn't send a constant stream of data. We would fill a buffer and slowly empty it over each loop of the main program. We decided the main program should only take input from one of these devices at a time, so a priority was built based around them, with the sensors being given the highest priority since they represent the most immediate danger to the vehicle, followed by the Bluetooth module, since that is the input coming from the parents, and then finally the joystick. If any input is received on the sensors or the Bluetooth module, we disable the joystick for about 2 seconds and then start to listen to it again. This is our final schematic design for our product. For our schematic, we used Eagle. It's a free product that's offered by Autodesk. In the far left, we have our voltage regulator. It's connected to the 2 pin holes that will have the solder connections of the battery, the positive and negative terminals. The voltage regulator is rated for between 4 and 30 volts, which is ideal as we expect most car batteries to be between 12 and 24 volts. The voltage regulator outputs a 5-volt signal that we'll use to power the microcontroller and most of the other devices on the circuit. The Bluetooth device and motor drivers, however, require a 3.3 volts, so we use a voltage divider circuit to output a 3.3 volt signal as well. Since we need to pass the batteries to the motors, we also leave a 24 volts line open that will be passed to the drivers. For our microcontroller to be programmed, we are going to use an SPI connection. It's also called a MISO-MOSI connector. We are using the programmer offered by Atmel to program the board, which uses a 6-pin layout that we have set a pin header for here. We also want a reset button in case we need to reset the device at any time during our final testing. However, on our final design, we'll most likely be removing both these from the board. We have a second pin header that will be used to connect to the joystick to read inputs for the x-axis, the y-axis, and the button inputs. These are all then fed to analog digital converters on the microcontroller. We have a third pin header that will connect to the various sensors around the cars that will then be fed into the microcontroller as well. We're using a Bluetooth integrated circuit that will output RX and TX serial values that are sent to the microcontroller for processing as well. This is the integrated circuit motor driver that is used in our final design, the Texas Instruments DRV8841PWPR. The IC takes in our battery input through the 24-volt line to VMA and VMB and outputs them to A out and B out respectively. The amount of voltage and current let through both these pins is controlled by the A in and the B in pins that are connected up to the pulse width modulation pins on the MCU. The AI and BI pins are used to control how much current is allowed through the module. In this configuration, with them both pulled down low, this allows as much current as possible to flow through the unit. The iSense pins are current sense pins that are used to detect the current throughput to the IC. The various resistors and capacitors that are used around the circuit are based on the datasheet specifications and their recommended values. This is our final assembled PCB board. The Bluetooth module and the IC motor driver are both disconnected for testing purposes. We also have several empty pins to add in and power the ultrasonic sensors that are on the car.
Hi, this is Miret Marzouk, and I will be talking about the application portion of our senior design project. As mentioned earlier, an essential part of our project is to implement an application that the children can use as a way to communicate with their parents and others, as well as the parents can use to control the car in case of emergencies. After talking to the children's families, we found out that each of the families use different types of smart devices. So we chose to develop a web application. Web applications are easier to develop, and when it comes to budget, it is way cheaper than mobile application, due to the fact that they don't require a developer's license to be deployed into an app store or Google Play. The application will have two types of users account, one for the children and one for the parents. The children's account will allow them to view flashcards with text and pictures of different items to choose from as a way to communicate with others. The parents' account will allow them to create different flashcards that can be accessed and viewed by their children. They will also have widgets to control the car in terms of steering, turning the car on and off in case of emergencies. For the application technology, the application will be developed using LAMP stack. LAMP stands for Linux, Apache, MySQL, and PHP. We chose LAMP stack over other stacks like MERN because it is one of the most popular stacks that have a lot of resources that we can reference. Also because most of our team members have previous experience with LAMP. We also used GoDaddy for our domain and web hosting because it is budget friendly.
Here is our GoBabyGo car app application interface. On the top left, you'll see our login page where the parents will be able to log in to the account. On the top right, you'll see the landing page where they can choose to go to the parents page, which is on the bottom left, which is the joystick interface where they can connect to the GoBabyGo car app and control it remotely. Or they can go to the child's page on the bottom right, which is the alternative communications page where the child can create flashcards and use them to communicate with others around them.
This is our budget. As you can see, we didn't spend much money on our PCB board. Motors were the most expensive part of our design, and the total cost so far is $104 only. In terms of challenges, the most challenging part was to design a system that fits the needs of all the families, as well as working with 4 different mechanical engineering teams and ensuring that our system is compatible with their designs. Each of the 4 mechanical engineering teams has to make a design for only one child, but our system must be suitable and compatible for each of their designs for the 4 children they're designing for. All the 4 of us are computer engineering major. We have no electrical major, so it was challenging to develop our BCB board. Finally, working with 4 different families and ensuring that we meet their needs and not their wants was so challenging because there was different requirements that each of the families wanted and not needed that would have made designing a system that fits all the needs of the other families more challenging.